Have you ever wondered what shape the universe takes when you zoom out far enough? Beyond our sun, beyond even our Milky Way, there exists a breathtaking cosmic architecture. Galaxies, islands of hundreds of billions of stars, each one a unique masterpiece painted across the darkness. Some spiral like cosmic hurricanes frozen in time. Others glow with the serene light of ancient suns. And some dance to their own rhythm, defying all patterns. Tonight, you and I will explore these magnificent structures and discover that the universe is not just vast, it is beautifully organized in ways that will leave you breathless. When you look up at the night sky, nearly every point of light you see belongs to our home galaxy. But scattered among those stars are faint, fuzzy patches that early astronomers called nebulae. For centuries, we wondered what they truly were. Were they merely clouds of gas within our own stellar neighborhood, or were they something far more profound? In the early 20th century, we discovered the truth. These were not clouds at all. They were entire galaxies, each containing billions or even trillions of stars, separated from us by distances so vast that their light takes millions of years to reach our eyes. The universe, we learned, is not a single island but an infinite archipelago. Galaxies are scattered throughout space like cities of light in an ocean of darkness. Each one is a gravitationally bound system, a cosmic ecosystem where stars are born, live out their lives, and die in spectacular fashion. The space between galaxies is almost perfectly empty, a void so complete that a single atom might drift alone for light years before encountering another. Yet within each galaxy, hundreds of billions of stars dance together in an ancient choreography governed by gravity and time. As we began to catalog these distant islands, we noticed something remarkable. Galaxies come in distinct shapes, each type telling a different story about its formation and history. Some are elegant spirals, their arms sweeping outward in graceful curves. Others are smooth ellipses, glowing with the soft light of ancient stars. And some defy easy classification, appearing chaotic and irregular, as if the universe itself was experimenting with form. This diversity is not random. Each shape represents a different chapter in the grand story of cosmic evolution. The man who first organized this cosmic zoo was Edwin Hubble, the astronomer who revolutionized our understanding of the universe. In the 1920s, he developed a classification system that became known as the Hubble sequence, a beautiful tuning fork diagram that arranged galaxies by their appearance. On one side, the ellipticals, from perfectly round to elongated ovals. On the other, the spirals, some with tightly wound arms, others with loose, sweeping curves. And at the edges, the irregulars, those cosmic rebels that refuse to fit any pattern at all. What Hubble could not have known at the time was that this sequence does not represent an evolutionary path. Galaxies do not begin as ellipticals and gradually transform into spirals or vice versa. Instead, each type emerges from different conditions in the early universe, shaped by the density of matter, the rate of star formation, and the violent interactions between galaxies over billions of years. The sequence is not a timeline, but a family portrait, showing the diverse outcomes of cosmic processes that have been unfolding since the first stars ignited in the darkness. Tonight, we will journey to each branch of the Hubble sequence. We will spiral through the arms of grand disk galaxies where new stars are being born at this very moment. We will visit the serene ellipticals, ancient and massive, where star formation ceased billions of years ago. And we will explore the irregulars, those wild and wonderful exceptions that remind us the universe never quite follows the rules we impose upon it. Each type has its own beauty, its own story, and each one holds clues to the greatest mysteries of existence. As we begin this exploration, I want you to imagine yourself not just as an observer, but as a cosmic traveler. We will move through space at speeds that defy comprehension, crossing distances that would take light itself millions of years to traverse. We will see these galaxies not as faint smudges of light, but as they truly are, magnificent cities of stars, each one a universe unto itself. Take a deep breath. Let your mind expand to encompass these vast scales and prepare to see the architecture of creation itself. Our journey begins at the very edge of the observable universe and will gradually bring us closer to home until we find ourselves looking at our own Milky Way from the outside. Along the way, we will witness phenomena that challenge our understanding of physics itself. We will see galaxies colliding in slow-motion ballets that take hundreds of millions of years to complete. We will discover supermassive black holes lurking at the hearts of these cosmic islands, and we will understand how everything we see, including the very atoms that make up our bodies, can be traced back to the life cycles of these magnificent structures. Let us begin with the most iconic type, the galaxies that have captured human imagination for generations. Spiral galaxies. These are the cosmic pinwheels, vast disks of stars rotating around a central bulge, their arms trailing behind like the wake of a boat moving through still water. They are perhaps the most photogenic objects in the universe, their structure so clear and defined that even amateur astronomers can discern their shape. But what creates these magnificent spirals? Why do they form these elegant arms instead of remaining as featureless disks? The arms you see are not solid structures rotating like the spokes of a wheel. If they were, the inner parts would complete their orbit faster than the outer parts, and the arms would wind up tighter and tighter until they disappeared. Instead, spiral arms are density waves, regions where matter temporarily becomes more concentrated as it moves through the disk. Imagine cars on a highway slowing down as they pass through a construction zone. The cars themselves move through, but the traffic jam remains in place. Spiral arms work the same way, creating persistent patterns in the flow of gas and stars. Spiral galaxies are factories of creation. Within their arms, vast clouds of hydrogen gas are compressed by the density waves, triggering the collapse of the gas into new stars. This is why spiral arms appear so bright and blue. They are filled with young, massive stars that burn brilliantly but briefly, living only a few million years before exploding as supernovae. Between the arms, the regions appear darker, populated by older, redder stars that have drifted out of the spiral pattern. The entire disk is alive with star formation, a process that will continue for billions of years to come. At the heart of every spiral galaxy lies a central bulge, a dense concentration of older stars that glow with a warm yellow light. This bulge is where the galaxy's supermassive black hole resides, an invisible monster with a mass millions or even billions of times greater than our Sun. Do not fear this darkness. The black hole is not actively consuming the galaxy. Instead, it sits quietly at the center, its gravity helping to hold the entire structure together. Only when material falls too close does it awaken, flaring with energy as matter spirals into oblivion. Not all spirals are created equal. Some, like the majestic Andromeda galaxy, have tightly wound arms that circle the core multiple times before fading into the outer halo. Others, like the graceful Triangulum galaxy, have loose, open arms that sweep outward in grand arcs. The tightness of the spiral pattern depends on the mass of the central bulge and the density of matter in the disk. Galaxies with massive bulges tend to have tighter spirals, while those with smaller bulges allow their arms to open wide, creating a more delicate appearance. Spiral galaxies are not alone in the universe. They often exist in small groups or massive clusters, interacting with their neighbors through gravity. Sometimes, two spirals will pass close enough that their outer stars and gas clouds are pulled into long tidal streams, connecting the galaxies like bridges across the void. These interactions can trigger bursts of star formation as the gravitational disturbance compresses gas clouds and ignites thousands of new stars. Eventually, over hundreds of millions of years, interacting spirals may merge completely, creating something entirely new. One of the most beautiful examples of spiral structure is the galaxy known as Messier 51, the Whirlpool Galaxy. This cosmic masterpiece has been photographed countless times, and each image reveals new details in its perfectly defined arms. What makes the whirlpool so striking is that it has a smaller companion galaxy interacting with it, pulling on its outer regions and enhancing the spiral pattern. The result is a galaxy that looks almost too perfect to be real, a testament to the organizing power of gravity and the inherent elegance of physical laws. As we observe these spiral galaxies, we are witnessing structures that have been rotating for billions of years, since a time when the universe was young and our solar system did not yet exist. The stars you see in the arms of distant spirals were born when the universe was still in its adolescence. The light we receive from them has traveled across the cosmos for millions of years, carrying information about a galaxy as it was in the distant past. We are not just looking at distant objects. We are looking backward through time itself, seeing the universe as it once was. Now, let us dive deeper, leaving behind the external view and plunging into the disk of a spiral galaxy to see what it looks like from within. Imagine for a moment that you could stand on a planet orbiting a star in one of these spiral arms. What would you see when you looked up at the night sky? The view would be spectacular beyond description. Thousands upon thousands of stars would fill your vision, some so bright they would cast shadows. The plane of the galaxy would stretch across the sky like a river of light. The space between stars in a spiral arm is not empty. It is filled with immense clouds of gas and dust, the raw material from which new stars will form. These clouds can be hundreds of light years across, containing enough matter to create thousands or even millions of stars. Where the clouds are densest and coldest, gravity begins to pull matter together. Pockets of gas collapse under their own weight, heating up as they contract. When the core reaches a temperature of millions of degrees, nuclear fusion ignites, and a new star is born. Star formation does not happen in isolation. When one massive star forms, its intense radiation and stellar winds compress the surrounding gas, triggering the formation of more stars nearby. The process cascades outward, creating entire clusters of stars that are all roughly the same age. These stellar nurseries are among the most beautiful sights in the galaxy, glowing with the light of newly ignited stars and painted with the vibrant colors of ionized gas. The Orion Nebula, visible to the naked eye from Earth, is one such nursery, a place where the future is being written in fire and light. The most massive stars born in these nurseries live fast and die young. They burn through their nuclear fuel in just a few million years, a blink of an eye on cosmic timescales. When their fuel runs out, they explode as supernovae, blasts so powerful that they briefly outshine the entire galaxy. These explosions scatter heavy elements into space, enriching the surrounding gas with carbon, oxygen, iron, and all the elements necessary for planets and life. Every atom in your body heavier than hydrogen and helium was forged in the heart of a dying star and dispersed by such an explosion. As we travel through the spiral arm, we encounter not just stars and nebulae, but also the dark lanes of dust that thread through the structure. These dust clouds absorb visible light, creating dark patches and filaments that contrast beautifully against the glowing gas. But if we could see in infrared light, these dark regions would come alive, revealing hidden star formation and the warm glow of dust heated by nearby stars. The galaxy is a tapestry woven from light and shadow, each element playing its part in the grand design. Between the spiral arms, the disk appears quieter, less dramatic. Here, star formation has slowed, and the light comes primarily from older stars that have drifted out of the density waves. These regions are not dead, merely resting. Gas clouds still float through this space, waiting for the next passage of a spiral arm to compress them into new stellar generations. The disk rotates inexorably, and everything within it moves through cycles of creation and dormancy, a rhythm that has persisted for billions of years and will continue for billions more. If we could speed up time and watch the spiral galaxy over millions of years, we would see the arms as waves washing through the disk. Stars and gas clouds would flow into the arms, brighten as new stars form, then drift back out as the density wave passes. The pattern itself would rotate, but more slowly than the matter within it. This is the dance of the spiral galaxy, a cosmic ballet choreographed by gravity, where the dancers move through the pattern, but the pattern itself endures. This is the environment in which our own solar system resides. We live within a spiral arm of the Milky Way, surrounded by the beauty and violence of ongoing star formation. The nearest stellar nursery to us, the Orion complex, is just over 1,000 light-years away. The nearest supernova remnant is much closer. We exist in a dynamic, ever-changing neighborhood, but one where the timescales are so vast that from our perspective, the sky appears eternal and unchanging. We are inside the very structures we have been admiring from afar. As we continue our exploration of spiral galaxies, we encounter a variation that is both common and fascinating. Large spiral galaxies. In these systems, the spiral arms do not emerge directly from the central bulge. Instead, they connect to the ends of an elongated bar of stars and gas that stretches across the core. This bar structure is not a rare anomaly. In fact, roughly 2/3 of all spiral galaxies, including our own Milky Way, are barred spirals. The presence of the bar profoundly affects how the galaxy evolves. The bar forms through an instability in the rotating disk. Galaxy spins, gravitational interactions between stars create a wave pattern that rotates more slowly than the stars themselves. This pattern locks in place, creating a bar-shaped region where stars orbit in elongated paths rather than circular ones. The bar acts like a cosmic highway, channeling gas from the outer disk toward the center. This influx of gas can fuel star formation in the core and feed the central supermassive black hole, affecting the galaxy's long-term evolution. Bars are not permanent features. Computer simulations suggest that they can form and dissolve over cosmic time. A spiral galaxy might exist for billions of years without a bar, then develop one as gravitational interactions organize its stars into the bar pattern. Later, interactions with other galaxies or changes in the distribution of mass might cause the bar to dissolve, returning the galaxy to a normal spiral configuration. This means that galaxies can transition between types, their appearance changing even though their fundamental nature remains the same. One of the most magnificent barred spirals visible from Earth is NGC 1300. This galaxy presents itself at an angle that allows us to see the bar structure clearly while also appreciating the sweep of its spiral arms. The bar glows with a golden light from older stars, while the arms are traced in blue by young stellar populations. At the very center, a tiny secondary spiral can be seen within the core itself, a spiral within a spiral, demonstrating that nature repeats its patterns at multiple scales. Living in a barred spiral like our Milky Way offers a slightly different view of the galactic landscape compared to a normal spiral. From our position, roughly 2/3 of the way out from the center, the bar appears as a dense concentration of stars in the direction of the galactic center. This bar channels material toward the core, where intense star formation creates bright stellar clusters. The bar also influences the orbits of stars throughout the galaxy, creating resonances that can affect the structure of the spiral arms themselves. The discovery that our own Milky Way possesses a bar was not made until the late 20th century. From our position within the disk, the structure is difficult to discern because we see it edge on, and dust in the galactic plane obscures much of the central region. Only by mapping the positions and motions of millions of stars using infrared observations were astronomers able to reveal the bar's presence. It was like discovering a hidden feature of our own home, a fundamental aspect of our galactic neighborhood that had remained invisible for centuries. The presence of a bar can make a spiral galaxy more efficient at forming stars, at least in its central regions. The bar acts like a funnel, directing gas inward where it accumulates and triggers bursts of star formation. This process can build up the central bulge over time, making it larger and more massive. Eventually, if enough gas is funneled into the core, it may feed the central black hole, triggering an active galactic nucleus phase where the galaxy's heart blazes with energy. The bar, then, is not just a structural feature, but an engine of galactic evolution. As we pull back from these barred spirals, we see them as they truly are. Elegant variations on the spiral theme, demonstrating that the universe is not content with a single design, but instead explores multiple possibilities. Each barred spiral is unique, with its own bar-length spiral arm structure and star formation history. Yet they all share the same fundamental physics, the same interplay of gravity, rotation, and matter that creates order from chaos. They remind us that beauty in the universe often comes from subtle variations on simple themes. Now we turn our attention to a very different type of galaxy. The ellipticals. Where spirals are dynamic and actively forming stars, ellipticals are serene and ancient. They appear as smooth, featureless clouds of light, with no spiral arms, no dust lanes, and very little ongoing star formation. They range from nearly spherical to highly elongated ellipses, but all share a similar characteristic. They are dominated by old red stars, giving them a warm golden glow. These are the retirement communities of the cosmos, places where the fires of creation have largely burned out. Elliptical galaxies are not simply scaled down or inflated versions of each other. They are classified by their apparent elongation, from E for nearly spherical ellipticals to E7 for the most elongated. But this classification tells us only about their appearance from our viewpoint, not their true three-dimensional shape. Some ellipticals that appear round might actually be elongated but oriented face onto our line of sight. Others might be flattened like footballs or discs, but oriented differently. The true shapes of ellipticals are diverse and sometimes surprising. The stars in elliptical galaxies do not move in orderly circular orbits like those in spiral disks. Instead, they follow random, chaotic paths like bees swarming around a hive. Some stars plunge toward the center on highly elliptical orbits, then swing back out to the periphery. Others move in more circular paths but at random orientations. This random motion is what gives ellipticals their smooth appearance. There is no preferred direction of motion, no organized rotation to create spiral arms or a flattened disk. The galaxy is held together purely by gravity, a swarm of stars bound by their mutual attraction. One of the most striking features of elliptical galaxies is what they lack. Where spirals are rich in gas and dust, the raw materials for new stars, ellipticals contain very little. Most of their gas was either consumed during earlier episodes of star formation or expelled by supernova explosions and stellar winds. Without fresh gas to collapse into new stars, star formation has effectively ceased. The galaxies shine only with the light of existing stars, which age and die without being replaced. Over time, ellipticals will grow dimmer as their stars exhaust their fuel. How do elliptical galaxies form? The answer lies in galactic collisions and mergers. When two spiral galaxies collide, their orderly disk structures are disrupted by gravitational interactions. The spirals lose their coherent rotation, and their stars are scattered into random orbits. Gas clouds collide and compress, triggering intense bursts of star formation that consume most of the available gas. What emerges from this violent process is an elliptical galaxy, a new structure built from the wreckage of spirals. In this way, ellipticals represent a later stage of galactic evolution. The largest galaxies in the universe are giant ellipticals, monsters with masses up to 100 times that of the Milky Way. These behemoths reside at the centers of galaxy clusters, having grown to their enormous size by cannibalizing smaller galaxies. They are the dominant members of their cosmic neighborhoods, their gravity pulling in and consuming any galaxy that ventures too close. Despite their immense size, they are relatively dim for their mass because they contain so little gas and few young stars. They are gentle giants, massive but quiescent. At the other extreme are the dwarf ellipticals, tiny galaxies containing only millions of stars rather than billions. These are among the faintest galaxies known, so dim that they are difficult to detect even with powerful telescopes. They are thought to be common in the universe, but most remain undiscovered because of their extreme faintness. Dwarf ellipticals often orbit larger galaxies as satellites, slowly being torn apart by tidal forces. They represent the small end of the galactic mass spectrum, reminding us that galaxies come in all sizes. Though ellipticals lack the dramatic beauty of star-forming spirals, they possess a serene elegance all their own. There is something profound about a galaxy that has exhausted its creative energy, that shines only with the accumulated light of billions of ancient suns. These are places where time moves differently, where the frantic pace of star formation has given way to a slow, graceful decline. In billions of years, when our Milky Way eventually merges with Andromeda, the resulting elliptical galaxy will join their ranks, a monument to the dynamic spirals that once were. Let us journey to the heart of a massive galaxy cluster and encounter one of the universe's most impressive objects, a giant elliptical galaxy. These titans can contain several trillion stars, making even our Milky Way seem modest by comparison. They dominate the centers of galaxy clusters, their immense gravity wells making them the gravitational anchors around which hundreds of other galaxies orbit. To approach one of these giants is to confront the true scale of cosmic structure, to understand that galaxies themselves can vary in size by factors of thousands. The most famous example is M87, a supergiant elliptical residing at the heart of the Virgo galaxy cluster. M87 is so massive that its gravity influences galaxies millions of light years away. But what truly makes M87 extraordinary is what lies at its very center, a supermassive black hole containing over 6 billion solar masses. This is the black hole, whose shadow was captured in the historic first image of a black hole's event horizon, a ring of light surrounding the darkness where gravity becomes absolute. Giant ellipticals are not passive objects despite their quiet appearance. Their central black holes can become active, accreting matter and launching jets of material at nearly the speed of light. These jets can extend for millions of light years, punching through the galaxy and injecting energy into the surrounding intergalactic medium. When a giant elliptical's black hole is active, the galaxy becomes one of the brightest objects in the universe at radio wavelengths. The jet from M87 is visible even in optical images, a luminous spike emerging from the galaxy's core. These giant ellipticals grow through a process called galactic cannibalism. Over billions of years, they consume smaller galaxies that stray too close. The smaller galaxy is torn apart by tidal forces, its stars scattered and incorporated into the giant's halo. This process leaves behind telltale signs, faint streams, and shells of stars that mark the disrupted remnants of past meals. Astronomers can read the history of a giant elliptical by studying these features, reconstructing the merger events that built the galaxy to its current size. At the very center of a giant elliptical, the density of stars is extraordinary. Stars are packed so closely together that collisions and near misses are common on astronomical timescales. In our solar neighborhood, the nearest star to the Sun is over 4 light-years away, and stellar collisions are essentially impossible. But in the core of a giant elliptical, Stars might pass within a few light days of each other. This creates exotic objects like blue stragglers, stars that appear younger than their surroundings because they formed from the merger of two older stars. Giant ellipticals are often surrounded by enormous systems of globular clusters, dense spherical collections of ancient stars. Where the Milky Way has about 150 known globular clusters, a giant elliptical like M87 possesses over 10,000. These globular clusters orbit the galaxy like a vast swarm of bees, each one containing hundreds of thousands of stars bound tightly together by gravity. The globular cluster systems of giant ellipticals may contain as many stars as entire dwarf galaxies, adding to the galaxy's already impressive total mass. The space between galaxies in a cluster is not empty. It is filled with extremely hot gas, heated to tens of millions of degrees by the gravitational energy of the cluster. This gas is so hot that it glows in X-rays, creating an extended halo around the central giant elliptical. The mass of this hot gas can exceed the combined mass of all the stars in all the galaxies in the cluster. It represents the majority of the ordinary matter in the cluster, most of which never formed into stars but instead remains as a hot, tenuous plasma. As we contemplate these giants, we must remember that they are not eternal. Over trillions of years, the stars within them will exhaust their fuel and fade. The galaxy will grow dimmer and dimmer as more stars die. Eventually, the only light will come from dying embers, white dwarfs cooling slowly toward absolute darkness. But this fate lies so far in the future that it is almost meaningless to contemplate. For now, these giant ellipticals reign as the monarchs of the cosmic hierarchy, monuments to the power of gravity to accumulate matter on truly staggering scales. Not all galaxies fit neatly into the categories we have discussed. Some refuse to conform to any regular pattern. These are the irregular galaxies, cosmic rebels that lack the symmetry of spirals and the smooth appearance of ellipticals. They are chaotic assemblages of stars, gas, and dust with no clear structure or organization. Yet they are not failures or mistakes. Irregular galaxies are important laboratories for understanding star formation and galactic evolution. They remind us that the universe is not always orderly, that beauty can emerge from chaos. Irregular galaxies come in two main varieties. Some, called I, show hints of structure, perhaps a single spiral arm or a bar that never fully developed. Others, classified as II, are completely chaotic, their appearance suggesting violent interactions or disturbances. Many irregular galaxies are small, containing only millions or billions of stars rather than hundreds of billions. Their low mass means their gravity is weak, making them susceptible to disruption by tidal forces from larger neighbors. They are the underdogs of the galactic zoo. Despite their small size, irregular galaxies can be remarkably active. Many are undergoing intense bursts of star formation, creating massive stars at rates that exceed those in much larger spiral galaxies. These starbursts are often triggered by interactions with neighboring galaxies or by the influx of fresh gas from the intergalactic medium. The resulting galaxies are ablaze with young, hot stars and glowing nebulae, painting the irregular structure in vivid shades of blue and pink. They may be small, but they burn bright. The closest examples of irregular galaxies are the large and small Magellanic clouds, satellite galaxies of the Milky Way visible from the southern hemisphere. These cosmic companions orbit our galaxy, currently located about 160,000 and 200,000 light-years away. They appear as faint, cloudy patches to the naked eye, like detached pieces of the Milky Way. Both are irregular in shape, with the large Magellanic cloud showing hints of a bar structure. They are actively forming stars, their irregular forms lit by the glow of stellar nurseries. The large Magellanic cloud contains one of the most magnificent stellar nurseries known, the Tarantula Nebula. a vast star-forming region containing hundreds of thousands of young stars. This nebula alone outshines entire galaxies, and the most massive stars within it are among the largest ever discovered. If the Tarantula Nebula were placed at the distance of the Orion Nebula, it would span 60 degrees of sky and be bright enough to cast shadows at night. It is a testament to the violent creativity possible in irregular galaxies. The irregular structure of these galaxies makes them vulnerable to the tidal forces exerted by larger neighbors. The Magellanic clouds are slowly being pulled apart by the Milky Way's gravity. Long streams of gas and stars called the Magellanic Stream and the leading arm have been stripped from the clouds and now wrap around our galaxy. Over billions of years, the clouds will likely be fully absorbed into the Milky Way, their stars becoming part of our galactic halo. They are galaxies in the process of being consumed. Some irregular galaxies are the products of galactic collisions. When two galaxies interact gravitationally, they can be distorted into irregular shapes, their orderly structures disrupted by tidal forces. The result is often a galaxy that looks like it was torn apart and reassembled incorrectly, with stars and gas scattered in chaotic patterns. These merger remnants are temporary. Over hundreds of millions of years, the stars will settle into new orbits, and the galaxy may eventually become a regular elliptical or spiral. But for now, they exist in a state of transformation. Irregular galaxies teach us that not everything in the universe follows rules. They show us that chaos can be just as creative as order, that some of the most intense star formation occurs in galaxies with no clear structure. They remind us that our classifications are human constructs, attempts to impose order on a universe that is far more diverse than our categories suggest. In their irregularity, these galaxies celebrate the cosmos's endless capacity for variation, for doing things differently, for surprising us with forms we never expected. Let us now travel to our closest galactic neighbors and explore them in detail. The large and small Magellanic clouds. These irregular dwarf galaxies have been known to humanity for millennia, visible to anyone in the southern hemisphere who looks up on a dark night. They are named after Ferdinand Magellan, whose crew documented them during the first circumnavigation of the Earth, though indigenous peoples of the southern hemisphere knew them long before. These clouds are not clouds at all, but entire galaxies, each containing billions of stars. The large Magellanic Cloud is about 160,000 light-years from Earth, making it one of the nearest galaxies to the Milky Way. It contains roughly 30 billion stars and has a mass of about 1/10 that of our galaxy. Though classified as irregular, it shows hints of structure, including a bar and a single spiral arm. This suggests it might have been a barred spiral galaxy before tidal interactions with the Milky Way disrupted its form. Now, it exists in a state between order and chaos, retaining memory of its former structure. Within the large Magellanic Cloud lies a cosmic treasure, the Tarantula Nebula we mentioned earlier. Also known as 30 Doradus, this is one of the most active star-forming regions in our local group of galaxies. At its heart is a cluster called R136, containing some of the most massive stars ever discovered. These stellar giants have masses exceeding 200 times that of our Sun and burn so hot that they glow with an almost bluish-white light. They live fast and will die young in spectacular supernova explosions. The large Magellanic Cloud has given us one of the most important astronomical events in recent history. In 1987, a star in the cloud exploded as a supernova, designated SN 1987A. This was the closest supernova to Earth observed in nearly 4 centuries, bright enough to be visible to the naked eye. Astronomers worldwide trained their telescopes on the event, capturing unprecedented data about how massive stars die. We even detected neutrinos from the explosion, ghostly particles that escaped the collapsing core and reached Earth hours before the light did. The small Magellanic Cloud, located about 200,000 light-years away, is even more irregular than its larger companion. It contains roughly 7 billion stars and has undergone significant tidal disruption from both the Milky Way and the large Magellanic Cloud itself. Its irregular shape and ongoing star formation make it a valuable laboratory for studying how galaxies evolve under the influence of external gravitational forces. Despite being smaller and less massive, it shines brilliantly with the light of young blue stars. Both Magellanic Clouds are connected by a bridge of gas and stars, evidence of their gravitational interaction with each other and with the Milky Way. This bridge is part of the larger Magellanic Stream, a vast trail of gas that extends over 600,000 light-years across the sky. The stream represents material stripped from the clouds by tidal forces, gradually being incorporated into the Milky Way's halo. It is a reminder that galaxies are not isolated objects, but interact dynamically with their neighbors over cosmic time. If we could view the Milky Way from the Magellanic Clouds, what would we see? Our galaxy would dominate the sky, a magnificent spiral spanning perhaps 30 degrees from end to end, roughly 60 times the apparent size of the full moon. The spiral arms would be clearly visible, traced by blue stars and pink nebulae. The central bulge would glow with a warm golden light. It would be the most spectacular sight in the night sky, a cosmic lighthouse illuminating the darkness. The Magellanic Clouds exist in the gravitational embrace of our galaxy. The future of the Magellanic Clouds is sealed. Over the next few billion years, they will continue their orbital dance around the Milky Way, gradually losing more gas and stars to tidal stripping. Eventually, they may merge with our galaxy entirely, their stars joining the Milky Way's halo. Or they might survive as disrupted remnants, ghost galaxies that have lost most of their mass. Either way, these companions have been with us for billions of years, and their presence has shaped our galaxy just as our gravity has shaped them. We have explored the different types of galaxies, but now we must ask a deeper question. How did these structures come to be? What processes shaped them into spirals, ellipticals, and irregulars? The story of galaxy evolution is one of the great triumphs of modern astronomy, a narrative that connects the first moments after the Big Bang to the rich diversity of galaxies we see today. It is a story written in dark matter, gas, and starlight, unfolding over billions of years of cosmic history. In the beginning, there were no galaxies. The universe was a nearly uniform sea of hot gas, primarily hydrogen and helium created in the Big Bang. But this uniformity was not perfect. Tiny fluctuations in density, quantum variations imprinted during the first fraction of a second, created regions where matter was slightly more concentrated. These overdense regions had stronger gravity, which pulled in more matter. Over millions of years, these small differences grew, creating the seeds from which galaxies would eventually form. The invisible scaffolding of galaxy formation is dark matter, a mysterious substance that interacts only through gravity. Dark matter began clumping together into halos long before ordinary matter could collapse into stars. These dark matter halos created gravitational wells into which gas could fall. As the gas fell inward, it heated and began to rotate. The rotation caused it to flatten into a disk, while the densest regions at the center collapsed to form the first stars. The basic architecture of galaxies was established by the interplay of dark matter and gas. The first galaxies formed about 400 million years after the Big Bang, ending the cosmic dark ages. These were small, irregular collections of stars, nothing like the grand spirals we see today. They were actively forming stars, blazing with the light of massive blue stars. Many of these proto-galaxies would merge with others, gradually building larger structures. Galaxy formation was not a single event, but a hierarchical process, with small galaxies merging to form larger ones, which in turn merged to form even larger structures. Spiral galaxies form when gas settles into a rotating disk and star formation proceeds gradually over billions of years. The key is to have a steady supply of fresh gas and relatively few major mergers. Each time gas clouds pass through the spiral arms, new stars form, maintaining the young blue population in the arms. The disk grows from the inside out, with the oldest stars concentrated in the central bulge and younger stars populating the outer regions. Spiral galaxies are the result of gentle, orderly evolution. Elliptical galaxies, by contrast, are born from violence. When two spiral galaxies collide, their delicate disk structures are destroyed. The gas clouds within them crash together, triggering intense star formation that consumes most of the available gas in a brief but spectacular starburst. The stars from both galaxies are scattered into random orbits, creating the smooth, featureless distribution we associate with ellipticals. The merger product may undergo several such collisions, growing larger each time, eventually becoming a massive elliptical at the center of a galaxy cluster. Galaxies do not evolve in isolation. They are connected by vast filaments of dark matter and gas that form the cosmic web, a network that spans the entire universe. Galaxies form at the nodes of this web, and gas flows along the filaments toward them, providing fuel for continued star formation. Galaxies in dense environments like clusters experience more interactions and mergers, evolving differently from those in the sparse cosmic voids. The environment in which a galaxy finds itself profoundly affects its evolution and final appearance. Understanding galaxy evolution requires looking back in time. When we observe distant galaxies, we see them as they were billions of years ago, when the light now reaching us first left them. By comparing galaxies at different distances, we can piece together how they change over cosmic time. We see that galaxies in the early universe were smaller, more irregular, and more actively forming stars than those today. The universe has been growing calmer as it ages, with star formation rates declining and galaxies settling into more regular structures. After journeying through the cosmos and exploring countless galaxies, it is time to return home and see our own galaxy with new eyes. The Milky Way. This is where we have always been, embedded within one of hundreds of billions of galaxies in the observable universe. We are part of this cosmic tapestry, not separate observers but participants in the grand story of galactic evolution. Understanding the Milky Way's place among galaxies helps us understand our place in the cosmos. The Milky Way is a barred spiral galaxy containing between 200 and 400 billion stars, along with vast amounts of gas, dust, and dark matter. Its disk is about 100,000 light-years in diameter, but only about 1,000 light-years thick in most places, making it extremely flat. We reside about 2/3 of the way out from the center, in a minor spiral arm called the Orion arm. From our perspective within the disk, we see the galaxy as a band of light stretching across the night sky, the combined glow of billions of stars too distant to resolve individually. At the very heart of our galaxy, hidden behind dense clouds of dust, lies Sagittarius. A supermassive black hole with a mass of about 4 million suns. Though we cannot see it directly in visible light, we can detect its presence through the orbits of nearby stars and through radio and X-ray emissions. This black hole is relatively quiet compared to those in active galaxies, but occasionally it flares when a gas cloud or wayward star ventures too close. It is the gravitational anchor around which our entire galaxy rotates. The Milky Way does not exist alone. It is the dominant member of a small group of galaxies called the Local Group, containing about 80 known galaxies within a region roughly 10 million light-years across. The other major member is the Andromeda Galaxy, a spiral slightly larger than our own, located about 2.5 million light-years away. The rest are dwarf galaxies, including the Magellanic Clouds and numerous faint satellites orbiting both the Milky Way and Andromeda. We are part of a small cosmic family. The Milky Way and Andromeda are on a collision course. They are moving toward each other at about 110 kilometers per second, and in roughly 4 billion years they will collide. Not worry. Collisions between individual stars are virtually impossible because the distances between stars are so vast. Instead, the two galaxies will pass through each other, their shapes distorted by tidal forces. They will swing apart, then fall back together again. After several such passages, they will merge into a single large elliptical galaxy. What will the night sky look like during this collision? From Earth, assuming our planet still exists and is still habitable, the view will be spectacular. Andromeda will grow larger and larger over millions of years, eventually dominating the sky. During the close passages, both galaxies will be severely distorted, their spiral arms stretched into long tidal tails. New stars will ignite in vast numbers as gas clouds collide. The sky will be ablaze with stellar fireworks, though the changes will occur too slowly for any human lifetime to perceive. Beyond the local group, the Milky Way is part of the Virgo supercluster, a larger structure containing thousands of galaxies spread across 110 million light-years. At the heart of this supercluster lies the Virgo cluster, dominated by the giant elliptical M87. The entire local group is falling toward the Virgo cluster, drawn by its immense gravitational pull. But we now know that even the Virgo supercluster is just one lobe of an even larger structure called Laniakea, a supercluster of superclusters spanning 500 million light-years. When we look at the Milky Way in this context, we see that we are part of structures nested within structures, scales of organization extending from stars to galaxies to clusters to superclusters. We are not at the center, nor are we at the edge. We are somewhere in the middle, residents of an average spiral galaxy in an average corner of the universe. Yet there is profound beauty in this ordinariness. We are connected to everything else, part of a cosmic web that links all matter and energy across the observable universe. We have looked back through time to understand how galaxies formed and evolved. Now, let us look forward into the distant future and contemplate what will become of these cosmic islands. The universe is expanding, and that expansion is accelerating. Over trillions of years, galaxies will drift farther and farther apart, isolated by the growth of space itself. The night sky of the far future will be vastly different from what we see today, lonelier but in some ways even more profound. Within individual galaxies, star formation will eventually cease. The raw materials for new stars, the vast clouds of hydrogen and helium gas, will be gradually consumed. Some will form stars. Some will be ejected from the galaxy by supernova explosions and stellar winds. Some will simply remain too diffuse and hot to collapse. Over tens of trillions of years, the last stars will form, and after that, galaxies will shine only with the light of stars that already exist. The era of star formation will end. As stars exhaust their fuel, they will die in various ways depending on their mass. Low-mass stars like our Sun will shed their outer layers as planetary nebulae, leaving behind white dwarf cores that will cool slowly over trillions of years. Massive stars will explode as supernovae, leaving behind neutron stars or black holes. Eventually, all that will remain are these stellar corpses, white dwarfs, neutron stars, and black holes. The galaxies will become graveyards, filled with the cooling remains of stars that once burned bright. On even longer timescales, the galaxies themselves will begin to dissolve. Occasional close encounters between stars will give some stars enough velocity to escape the galaxy's gravity entirely. Over periods measured in googol years, galaxies will gradually evaporate, losing their stars one by one to the void. What remains will be the most tightly bound objects, stars orbiting very close to the central supermassive black hole, and systems like close binary stars. But even these will not last forever. Black holes, those seemingly eternal objects, will themselves eventually die. Through a quantum process called Hawking radiation, black holes very slowly evaporate, returning their mass to the universe as thermal energy. The evaporation rate is incredibly slow. A solar mass black hole would take longer than the current age of the universe just to lose a tiny fraction of its mass. But given enough time, even the supermassive black holes at the centers of galaxies will evaporate completely, leaving nothing behind. In the ultimate far future, after all stars have died and all black holes have evaporated, the universe will enter what physicists call the black hole era, and eventually the dark era. Space will be nearly empty, filled only with photons, neutrinos, and occasional electrons and positrons. The temperature will approach absolute zero. Nothing will happen because there will be no concentrated energy left to drive any processes. The universe will have reached a state of maximum entropy, a cold, dark equilibrium from which nothing new can emerge. These timescales are so vast as to be almost meaningless. The current age of the universe, about 14 billion years, is nothing compared to the trillions and googles of years we are discussing. All of human history, all of recorded civilization, is less than an eye blink compared to these eons. Yet there is something strangely comforting about this perspective. It reminds us that the universe we see today, vibrant and alive with star formation, is a temporary phase, a brief flowering in the long cosmic story. We are privileged to live in an era when the universe is still young and active, when galaxies are still forming stars and evolving. In a sense, we exist at a special time in cosmic history, early enough that the sky is filled with galaxies and late enough that heavy elements and complex chemistry have made life possible. Future civilizations, if any exist, trillions of years hence will look out on a very different universe, one growing cold and dark. They might envy us our star-filled skies. We have completed our journey through the realm of galaxies, exploring spirals, ellipticals, and irregulars, understanding how they form, evolve, and eventually fade. But what does all this mean for us? Why should we care about structures so distant that their light takes millions of years to reach us? The answer lies in the fundamental connection between galaxies and ourselves. We are not separate from these cosmic islands. We are made of them. Every atom in your body was forged in the heart of a star. The carbon in your cells, the iron in your blood, the calcium in your bones, all of these elements were created by nuclear fusion in stellar cores and dispersed by supernova explosions. You are literally made of stardust, assembled from the debris of stars that died billions of years ago. The galaxies we have explored are not just objects of study. They are the furnaces in which the raw materials of life were created. Understanding galaxies helps us understand our place in the cosmos. We live in an ordinary spiral galaxy in an ordinary corner of the universe. There is nothing special about our location, yet this ordinariness is itself profound. It means that what happens here likely happens throughout the cosmos. If life and intelligence arose here, they probably arose elsewhere too. We may be one of countless civilizations scattered across billions of galaxies, each looking out at the universe and wondering if they are alone. The study of galaxies also teaches us humility. When you grasp the true scale of the universe, with its hundreds of billions of galaxies each containing hundreds of billions of stars, it becomes impossible to believe that everything was created just for us. We are a tiny part of something incomprehensibly vast, a single planet orbiting a single star in one galaxy among countless others. Yet we are part of it. We are the universe, looking back at itself, matter that has become conscious and capable of understanding its own origins. There is also practical value in studying galaxies. Understanding how galaxies evolve helps us understand how our own Milky Way formed and what its future holds. Studying active galactic nuclei teaches us about the physics of black holes and extreme gravitational fields. Observing distant galaxies allows us to look back in time and understand the history of the universe itself. Every discovery about galaxies is a discovery about the fundamental nature of reality. Perhaps most importantly, galaxies inspire wonder. There is something deeply moving about seeing an image of a distant galaxy, knowing that you are looking at billions of suns, each potentially surrounded by planets, all bound together by gravity across distances your mind can barely comprehend. This sense of wonder is valuable in itself. It reminds us that the universe is larger and more beautiful than our everyday concerns, that there is something beyond ourselves worth contemplating. As our technology improves, we will learn more about galaxies than ever before. New telescopes will allow us to see the first galaxies that formed in the early universe. We will map the distribution of dark matter and understand how it shapes galactic evolution. We may even detect signs of life on planets orbiting stars in distant galaxies, though such detection would require technology far beyond our current capabilities. The study of galaxies is not finished. It is only beginning. When you next look up at the night sky, remember what you have learned. Those faint smudges of light are not mere clouds of stars. They are galaxies, entire universes unto themselves, each with its own history and character. Some are spirals like our home, dynamic and alive with star formation. Others are ancient ellipticals, serene cities of elderly suns. And some are chaotic irregulars, cosmic rebels dancing to their own rhythm. All of them are part of the magnificent tapestry of the cosmos, and so are you. Our exploration of galaxy types has come to an end, but the story continues in the sky above you every night. The next time you find yourself under the stars, take a moment to appreciate the vast structures that fill the universe, the spirals and ellipticals and irregulars that together form the cosmic architecture of creation. Remember that you are connected to all of it, made from the same matter, governed by the same laws. In understanding galaxies, we understand ourselves and our place in the grand cosmic story. What will you see when you next look up?